Single population inference. Problem 1. Increasing number of both private and public agencies are requiring their employees to submit to tests for substance abuse. One laboratory that conducts such testing has developed a system with a normalized measurement scale in which value less than 1 indicate normal range, and values equal to or greater than 1 are indicative of potential substance abuse. The lab reports the normal result as long as the median level of an individual is less than 1. Independent measurement of each individual sample are made. One individual result are shown in table 14.1. For this individual was taken, we're doing a different test using the urine or maybe blood test. They obtain a different result from this sample, and we want to know if this evidence is enough to assure that the mean or the median, this value is less than 1. Why we talk about here median instead mean? Because this is a non-parametric procedure. Remember, we can obtain the median or the mean of this value, and we can, because we can test the hypothesis about if the mean is less than 1 or less than or greater than 1, but we cannot use here the t-distribution, because to test hypothesis about the mean, we use t-distribution when my sample is small, or z-distribution when my sample is bigger than 30. But we can use t-distribution for a small sample only when the population is normally distributed. We don't know here if we have a normal distribution. Actually, you can observe here this value. This value is an outlier. When we have an outlier, the distribution is not normal, it's skewed to, in this case, it's skewed to the right. Then we cannot use the t-test that we used previously to test the hypothesis about the mean of the population, because we need the assumption that the population is normally distributed. In this case, it's not normally distributed, it's skewed to the right. But we can test hypotheses about the median, and the assumption for this test is that the random variable is continuous, and we are going to assume that 50% of the population is below the median and the other 50% is above the median. The only assumption, doesn't matter the shape. If we have this population, and in the population we assume that the median, we denote the median by this letter, is equal 1, then 50% of all value will be above 1 and 50% will be below 1 in this population, for this person. However, if we suspect that the median is smaller than 1, then when we take a sample from this population, when the median is not located here, is located here, then it's possible, for sure, we are going to obtain more value less than 1. That is our expectation. That is the idea. We are going to count the number of success, the number of value less than 1, which support that the median should be less than 1. First of all, with this data, we can solve this problem in StatCrunch. Let's send my data to StatCrunch automatically, and this is my data, substance abuse. Then we have my data in this column. Let's select stat, non-parametric procedure, and sign test. It's very simple. Then where is located my data? My data is located in this column with the name is substance abuse test result. And what is the hypothesis test? We assume that the median of all of this value is 1, but we want to find evidence that is smaller than 1, then smaller than 1. That is my alternative. And compute. Then from 8 different results, 1, 2, 3, 4, 8, 7 are below than 1. What is the p-value of this test? What is the probability? In 8 different trials, we get 7 below 1. That is the probability to get 7 below 1. The p-value actually is the probability to get this value 7 7 or one value more extreme in the direction of my alternative. The alternative is less than 1. To obtain 7 value less than 1, in this case 7 value below than 1, the probability to get 7 value below than 1 in a different trial is 0.035, 3.5% of the cases. That is the p-value. Actually, because this p-value is smaller than alpha, we reject the node. The alpha in this case is 5%. Then it's very strange that we obtain 7 value below the mean. Then we reject the assumption that the mean is below 1. And maybe this person doesn't pass the test, but we have 1 value above. Then let's obtain the same result using formulas and table to show you work in this problem. Then that is the printout in StatCrunch, and this is the printout in SPSS. This is the same. The p-value is 3.5, 0.035. It's smaller than 0.05. We can use two different tables. In Canva, you can find these two different tables. In one table, we have the probability to get exactly from a trial to get 0 success, 1, 2, 3. This is the individual probability. Or we can use this other table. We have the cumulative probability. In this case, for example, in a trial, when the probability of success is 50%, in this column we have the cumulative probability. This is the probability to get 0 success. Here we have probability to get 0 and 1 success. When we sum these two, we obtain 0.035. And here is to obtain the probability of 0 success, 1 success, and 3 success. This is the sum of these three values, 0.04, 0.031, and 0.109. When we sum these three values, we will obtain 0.145, and so on. The probability to get a success is actually the cumulative probability is 100% of the cases. When we sum all of this probability, including probability to get a success exactly, when we sum all of this, we will obtain 1. Okay, we can use any of these two tables. If we use the first table, when we have the individual probability, then we have, this is our data. The first thing that we need to do is count how many values are below 1, because we assume that the median is 1, then 50% of the value, we expect 50% of the value below 1. But let's count how many values we have below 1. We can order this value, and when we order this value, we can observe that below 1 we have 7 of these. Only one value is above 3.79. We can do that in Excel. We can organize this value in Excel using Excel. In Excel, the only thing that we have to do is send this value to Excel, select these values, and go to data, and in data sort this value, and let's click OK, and we have the value already organized. We have 7 values below 1 and only 1 value above 1. Let's return. Then, given that, let's find the p-value of this evidence. Get 7 value below 1, assuming that the median is 1. Then the probability, the number of trials is A. The probability of success to get 1 value below 1 is 50% of the cases. And we want to obtain the probability to get 7 value or A value. In this case, the probability to get 7 or 1 value more extreme in the direction of my alternative. The alternative is below 1, in the direction smaller than 1. Then the probability to get 7 value or more value less than 1, in this case we did only a trial, is only 2 cases, 7 and 8. Then in this table, the probability to get 7 value below 1 is 0.031, and the probability to get A is 0.04. Actually, those probability could be obtained using the binomial formula. The binomial formula is this: the probability to get exactly 7 value is from A trials. We want to obtain 7 value. Order doesn't matter. Probability of success must be raised to 7 power. Probability of failure to 1 power. Then A combination 7 is equivalent A factorial divided by 7 factorial. A minus 7 factorial is 1 factorial. Probability of success is 0.5 raised to the 7 power. Probability of failure is the complement of probability of success raised to the 1 power. Then we can transform this in A times 7 factorial over 7 factorial. We can cancel this, and when we do all of this multiplication, then we can obtain this value. Exactly, 7 success is 0.031. That is exactly the probability to get 7 success. We can compute the probability to obtain a success using the same formula, and we will obtain this other value. Then that is probability to get 7 success. The probability to get a success is 0.04. Then the probability to get 7 or more success is the probability to get 7, and the probability to get a. We add this probability, and the probability is 0.85. If we use the other table, the cumulative table, then the probability to get 7 success in this column, probability of success is 50%. A doesn't appear because the cumulative probability indicate that the sum of all of this probability must be equal 1 here. Then in this column, for a success, the sum should be equal 1. The cumulative should be equal 1. Then the probability to obtain in a trial 1 success or 2 or 3 or 4 or 5 or 6 or 7 or 8 must be equal 100% of cases. Then the probability to get 7 or more success could be obtained 1 minus all of this. But when we sum all of this probability, actually in this table is the cumulative probability until 6 is given in this table by this number. That is the cumulative until 6. Then the probability to get more than 7 is equivalent to obtain 1 minus probability to get less or 6 success. This probability is given by actually the same value that we obtained in the previous result. Also, we can use a StatCrunch. In a StatCrunch, we need to go to calculator, and in calculator, let's go to binomial. In binomial, we need to input here the number of trials, which is A. Here, the probability of success, that is 50%. Here, greater than, because we want to obtain p-value, probability to get the value in my evidence that was 7 or one value more extreme. 7 and A is the more extreme value. Then the probability to get 7 or more success, when we click compute, we obtain exactly the same p-value. And let's show our work. Then first of all, we need to write the null and the alternate hypothesis. The null hypothesis is the assumption that the median is equal 1, and the alternative is the median is smaller than 1. We want to obtain evidence that is smaller than 1, and we conduct our trial. We count in our test the number of values that are smaller than 1. That is my test statistic, and we compute the p-value for this result. What is the probability to get more than 7, or one value more extreme than 7? 7 or more extreme than 7 is equivalent to 3.5%. We did it already. And because this p-value is smaller than alpha, we reject the null. What is the null? That the null assumes that the median is equal 1. We have to reject that, and we need to support that is different. Actually is greater than 1. Let's stop here.